Hello friends, welcome to Namagiri's channel, and in this video I'll be discussing why the solution of a linear programming problem using graphical method occurs at one of the boundary boundary points, or rather the vertices of the feasible region. Sometimes it does occur along one of the full segments uh, that composes this feasible region, but in general it occurs at one of the vertices of the feasible region. So now, in order to discuss this problem, I have taken a specific example. The general proof is quite similar to the proof that I will be presenting in this special case. So this special case is as follows. This is the typical linear programming problem. We want to maximize this objective function z equal to 5x plus y, and the constraints given are 2x plus y less than or equal to 6, x plus y less than or equal to 4, and x and y are both non-negative. Okay, so here I have drawn the corresponding diagram. Okay, so this is the line x plus y equal to 4, and the region that lies toward the origin represents this equation, x plus y less than or equal to 4. Okay, second is 2x plus y equal to 6 is this line with 6 as the y-intercept, and the region again that lies toward the origin represents this inequality, and x greater than or equal to 0 and y greater than or equal to 0 imply that we are considering the first quadrant. So therefore the feasible region is this. This is the feasible region that we have to understand. Okay, fine. So, and this point of intersection of these two lines is 2, 2. You can verify that here. So we have 4 vertices over here for this feasible region. One is 0, 0, the second is 0, 4, third is 2, 0, and then 2, 2, and the last one is 3, 0. Okay, so the solution will occur at one of these vertices. That is what we know. Fine. So how are we going to prove this? Why does the maximum never occurs in at a point that lies in the interior of this feasible region? That is what we shall prove first. So let us take a point that lies in the interior of this feasible region. Let's take this point 2, 1. Sorry, 1, 2. All right. Let me now just erase or rather wipe out these lines. I don't want them to interfere with our other drawings. Fine. So this is our point that is under consideration. All right. Now what I will do is I will draw a line that passes through 0, 1 and 1, 2. Let us extend this line on both the sides, but the portion of this line that interests us is the one that lies inside the feasible region, because the part that lies beyond the feasible region is of no relevance to us. Therefore, let's focus on the segment that lies in the first of all, this segment that lies along this line, and that the part that lies inside the feasible region. So this is the segment. Now how does the objective function vary along this segment? That is what that is what is crucial to our analysis in this case. So let's see, first let us find out the equation of this line. First observe that the slope of this line is 1, and the second thing to observe is that its intercept, y-intercept, is positive 1. So therefore the equation of this line is y equal to slope multiplied by x, which is 1 multiplied by x plus the y-intercept, which is 1 in this case. Okay, fine. Now this is the relation between x and y along this line. Okay, so now in order to find out how the this objective function behaves along this line, we can substitute for y using this equation. So z along this line, let's call this line as line L1, let's say. Z along L1. How does z behave, or how it behaves along this line L1 is 5x plus y, but y is x plus 1 along the line L1. So therefore we can substitute for y as x plus 1. So this is 6x plus 1. Now the objective function, which was earlier the function of two variables, has now become a function of only one variable, which is x. What does this mean? This can help us to find out where z takes maximum value and minimum value along this line, or rather on this segment. Observe that as x increases, the value of x coordinate increases, z will increase because the coefficient of x is positive. Okay, so now on this segment, as we travel in this direction, the x coordinates of the points increase, and therefore the objective function, the value of the objective function also increases, and therefore the maximum is attained at the end of this segment, which lies on the boundary point over here. So here the the value of the objective function at point 1, 2 is certainly less than the value of the objective function at this point, because objective function is increasing in this direction, since value of x coordinate is increasing in this direction. Okay, fine. So this is the first thing. Now, and why is this happening? Because the coefficient of x is positive over here, but here we are considering this line. There are in fact infinitely many lines that pass through this point. It may happen that the coefficient of x is negative, or even sometimes it may be 0. For example, consider this point, which is 1.25. Okay, I have already premeditated these things, therefore I am giving it to you readily. So 1.25, and let us draw a line that passes through these 2 points. Extend that. Okay, now what is let us call this line as L2. This line L2 is passing through the point 1, 2 and 1.25, 0, and the equation of this line, this is L1, this is L2, is y equal to negative 8x plus 10. You can verify that the equation of the line passing through these 2 points, this is 1.25 comma 0. Okay, now along this line L2, let's see what is the how the objective function varies. Now here y is equal to negative 8x plus 10, so we can substitute for y in this equation. 5x plus y now becomes which is negative 3x plus 10. Now observe that the objective function here is negative 3x plus 10. So therefore, as x increases along this line, the objective function decreases. So in this feasible region, this is the boundary point, and this also is the boundary point, and the x coordinate of this point is larger than the x coordinate of this point. You observe it carefully. So the x coordinate is increasing as we go downward. All right, fine. And therefore the function value of the objective function decreases as we go downward. Okay, because x is increasing in this direction. Therefore the maximum is over here, and as we progress along this line, it attains minimum over here. Fine. So the maximum is over here. So what is the moral of the story? When we considered line L1, the maximum of the value of objective function was at this boundary point. When we considered another line L2, the maximum attained was at this boundary point. So you take any line in general, the maximum will always be attained at one of the points lying along the boundary. Okay, consider that segment and analyze any segment that lies inside the feasible region, and the maximum will be attained at one of the endpoint, and the minimum will be attained at the other endpoint of the objective function. So we have progressed quite a bit toward what we want to prove. Okay, great. So what is the next step? So now this means that we need not consider any point that lies in the interior of the feasible region, because the maximum of the maximum value at the maximum value of the objective function at the boundary points will always be greater than or equal to the value of the objective function in the interior point. Okay, so we need to consider only the value of the objective function at the boundary points. So we have actually kicked out the whole of the interior of the feasible region, and now we can focus only on the segments that compose the whole boundary of the feasible region. Now, why only vertices? How can we get rid of the even the edges of the feasible region? Now observe that in the same way as we argued for this segment, and we argued that the objective function increases in either of the direction, in this direction or in this direction, we can argue in the same way for the segments that comprise the feasible region. For example, this edge is a part of the feasible boundary of the feasible region. This edge also is the part of the boundary of the feasible region. We can argue in the same way and say that the objective function either increases in this direction or decreases in this direction. If it increases in this direction, then the maximum value is attained at this point, or if it decreases in this direction, then the maximum value is attained at this point and minimum is attained at this point. So therefore, in order to find out where the maximum is attained, we need to check only the vertices, the value of the objective function at the vertices of the feasible region. So practically the proof is complete over here. Sometimes it may even happen that if the coefficient of x is 0, then the objective function is constant along a certain segment, and in that case the optimum value, that is either maximum value or the minimum value, is constant for the whole segment, the points on the whole segment, and the whole segment is a solution. So I hope that this completes the proof. If you have any difficulty or doubt, then please pause and rewind and go through it once again. And okay, I shall stop here, and thank you for watching the video. If you enjoyed this video, then please share it with your friends and subscribe to the channel. Okay, see you in the next video. Bye.